lecture 20, and I want to review and do some homework problems from the two sections we've done so far in chapter 3, which are sections 1 and section 3. And let's take a look. So we're interested in just the field of congruence classes modulo P, where P is a prime number. And we say the following, slightly more generally, but I'll specialize it to a prime in a moment. So this is the definition of what is called a kth power residue. So let M, K, and A be integers. Where M is going to be the modulus, at least 2. K is a kth power, K is at least 2. And A and M are relatively prime. So we say that A is a kth power residue, modulo M, if there exists an integer x such that A is a kth power mod n. That means A is congruent to x to the k mod m. So kth power residue is the same as kth power, but we're looking at residue classes modulo m. And the most important case for us is k equals 2. So we're looking at squares. And we say A is a 2th power residue, but we use the word quadratic instead of 2th, is a quadratic residue modulo m if there exists an integer x such that A is a square, A is x squared mod m. So just as with ordinary integers, not every integer is a square. 9 is a square, plus 9 is 3 squared. 10 is not a square, because 10 is not x squared for any integer x. So just as with integers, in the case of integers, some integers are squares and some are not. When you're looking at congruence classes modulo m, some congruence classes are squares and some are not. And there's a very important general theorem that gives a kind of a condition for a number to be a kth power residue. And let me go over that. So this is Theorem 311. And we're just going to look at moduli that are prime. So let P be a prime number. K, that's going to be the kth power we're looking at. And we define D to be the greatest common divisor of K and P minus 1. So we have a modulus P that's a prime. We're looking at kth powers. and D is the greatest common divisor of K and P minus 1. That A be an integer which is not divisible by P. Another way of saying that is A is not congruent to 0 mod P, right? This means P doesn't divide A. So the theorem says then A is a kth power residue if and only if the index of A with respect to G is congruent to 0 mod D, where G is a primitive root. So I should say that A, B, and Z are not congruent to 0 mod Z. Let G be a primitive root mod P. Then A is a kth power residue if and only if the index of A with respect to G is divisible by D, which is the same as saying, this is all part of the theorem, A to the power P minus 1 over D is 1 mod P. And so this is the first part of the statement of the theorem. And the second part says that if in fact A is a kth power residue, mod P, then the congruence x to the k congruent to A mod P, right? So if A is a kth power residue, that means there exists at least one K that satisfies this congruence. And in fact, there are exactly D pairwise incongruent so this has exactly D pairwise incongruent solutions. So if x to the k is A, that's like saying x is a kth root of A. And just the way in the reals, for example, a number typically will have, if it has a square root, it will have 2 square roots. If a number has a kth root, it will have D kth roots. So if A is a kth power residue modulo P, then this congruence has exactly D pairwise incongruent solutions. And the number, so this is actually the third statement. So the number of kth power residues mod P is exactly P minus 1 over D. So there really are 3 important parts of this theorem, and I'm going to prove them. But again, let me just remind you, what is a primitive root and what is the index of a congruence class with respect to a primitive root? So there's a theorem. So it says the following: G is a primitive root modulo the prime P if whenever you look at all the congruence classes different from 0 in Z mod PZ, so this is 1 plus PZ, 2 plus PZ, 3 plus PZ, up to P minus 1 plus PZ. So these are the P minus 1 non-zero congruence classes mod P. You can represent each of these as a power of G. This is G to the K plus PZ, where K goes from 0, 1, 2, up to P minus 2. So every non-zero congruence class is a power of G. So equivalently, if A and P are relatively prime, then there exists a K 0, 1, 2, up to P minus 2, such that A is congruent to G to the K mod P. Right? So a primitive root mod P is a number such that every non-zero congruence class mod P is a power of G. And this K is unique. There's just one K in this interval, and we write or call K is the index, IND for index, of the integer A with respect to the primitive root mod G. Okay, so, and the big theorem in section 3.1 it's actually a corollary of, oh, sorry, it was 3.4. That was the number I assigned to it. Every prime P has a primitive root. And in fact, it has exactly phi of P minus 1 primitive roots.
Professor.
Yeah.
In the set of K, what's that P minus at the very end? Is that a 2?
Yeah. Up to P minus. So there are P minus 1 numbers in this set. They go from 0 to P minus 1.
Okay.
So for example, G to the 0, that's just 1 mod P. G to the 1 is whatever is G mod P. And so forth. G to the P minus 2 is whatever it is mod P. But G to the P minus 1, well, for a prime, phi of P is P minus 1. So this is G to the phi of P. And by the Euler-Fermat theorem, this is congruent to 1 mod P. So if I keep taking powers of G, I get to the P minus second power. When I take G to the P minus first power, that brings me back to 1.
Understood.
By Euler's theorem.
And you don't want that.
Well, no, it's perfectly fine, but I want to, the point is that every integer that's not divisible by P is congruent to a power of G. And because of Euler's theorem, the powers, you can write it as a non-negative power between 0 and P minus 2. You don't have to take any bigger number. And because they're P minus 1 congruence classes relatively prime to P, you need all of these numbers. So for example, if you take P equals 7, G equals 3, is a primitive root, right? G to the 0th power is 1. Sorry, 3 to the 0 is 1. 3 to the 1st power is 3. 3 squared is 9, is 2. 3 cubed is 27, is 6, mod 7. 3 to the 4th is 81, is 4, mod 7. 3 to the 5th is 729, is
5, no? To complete the, shouldn't it be 5 to complete all the residues?
right. Let me, yeah, because 3 to the 5th is 243. And if you divide that by 7, you get a remainder of 5. And p minus 1 is 6. 3 to the 6th is 729, is 1 mod 7, just the way Euler's theorem says it has to be. So we take the powers of g to the k going from 0, 1, 2, 3, 4, and 5. This gives you all of the classes, 1, 2, 3, 4, 5, and 6, mod 7. And 5, that's p minus 2, 7 minus 2. You only go up to p minus 2. So that's just a reminder of the definition of a primitive root modulo a prime and the index of a primitive root modulo a prime. And we have to go and now prove our theorem. This was the theorem. And it says if you take a prime number p and you define and you take an integer k, at least 2, and you let d be the greatest common divisor of k and p minus 1, the first question is, how can you tell what is a criterion to determine if an integer a is a kth power residue? And the first part of the theorem says a is a kth power residue if and only if the index of a with respect to a primitive root g is divisible by d, or if and only if a to the power p minus 1 over d is congruent to 1 mod p. So let's see if I can prove this first statement. So let d be the greatest common divisor of k and p minus 1. Let L, so we know a and p are relatively prime, so let L be the index of a with respect to the primitive root g. So this means that a to the L, g to the L, is congruent to a mod p. All right, that's the definition of the index. And so x to the k, there exists an x such that x to the k is congruent to a mod p if and only if there exists a y such that x is g to the y mod p. Every number relatively prime to p is a power of g, and x to the k congruent to a mod p is the same as g to the y to the k, because x is g to the y, congruent to a, which is g to the l mod p. G to the y to the power k, just the way they teach you in elementary school. This is g to the k times y. So this congruence has a solution if and only if there's an integer y that satisfies this congruence. And the order of g mod p is p minus 1. So this is true if and only if ky is congruent to L mod p minus 1. That is, A is a kth power residue if and only if this congruence has a solution. But this is a linear congruence, and this has a solution if and only if L is congruent to 0 modulo the greatest common divisor of p minus 1 and k, which is d, L congruent to 0 mod d. And L is the index of A with respect to G. So the index of A with respect to G has to be divisible by D. So A is a kth power residue if and only if the index of A is congruent to 0 modulo D. So the kth power residues mod p are exactly the numbers A whose indices are multiples of D. So the kth power residues are 1, which is g to the 0, g to the d, g to the 2d, all the multiples of d, and the largest multiple of d less than or equal to p minus 1 will be p minus 1 over d minus 1 times d. So these are the dth powers of g to the d. Right? All the different powers of g to the d between 0 and less than p minus 1. And there was another condition equivalent to what we just proved for a kth power residue, and that's the following. So let's say A is a kth power residue mod P if and only if A is congruent to G to some multiple of D. Sorry, some multiple of P minus 1 over D. Mod P. It's a little bit more legible. So the kth power residues are the G to the Dth powers, things of the form G to the power D times I. So if A is an integer of this form, then A to the D is G to the P minus 1 over DI to the D. That's G to the P minus 1. The D's cancel times I. G to the P minus 1 is 1 mod P. Oops. Let me say this properly. Let me say it this way. So what are the kth power residues? They're the powers of G to the D. So A is a kth power residue mod P if and only if A is congruent to G, the primitive root, to a power D times I mod P. And if this is the case, then A to the power P minus 1 over D is G to the DI to the power P minus 1 over D. This is G to the power D times I times P minus 1 over D. The D's cancel. This is G times I times P minus 1. G to the P minus 1 is 1 mod P. So if A is a primitive root, sorry, if A is a kth power residue, A to the P minus 1 over D has to be 1. Or another way of saying this is because the index of A with respect to G is L, A is congruent to G to the DI mod P. So A is G to the L. So L I just want to say this the way I did in the text, so it's easier to follow. Let me just do it in the following way. So what I just showed is that if A is a kth power residue mod P, then A to the power P minus 1 over D is congruent to 1 mod P. Conversely, suppose that A to the power P minus 1 over D is congruent to 1 mod P. So we know that A is congruent to G to the L mod P. So A to the P minus 1 over D is congruent to G to the L to the P minus 1 over D, is congruent to 1 mod P. But the smallest power of G, that's 1 mod P, is P minus first. So L times P minus 1 over D, that's an integer. This has to be congruent to 0 modulo P minus 1. Which happens only if L over D is an integer, which is the same as saying that L is congruent to 0 mod D, which is the same as saying that A is a primitive root. And finally, one other point. So A congruent to G to the L mod P is a kth power residue if and only if there's a y such that ky is congruent to L mod P, and this congruence has exactly how many solutions? It has exactly, sorry, mod P minus 1. This has exactly D equal to greatest common divisor of K and P minus 1 solutions. And for every such y, we have a solution of the congruence, A congruent to G to the y times K mod P. So this is a kth power, it's the kth power of G to the y, and they're exactly D such y's. So every A that's a kth power has D kth roots. So let's just see what this says in what for us is the most important case, also the simplest case, K equal 2. So we're interested in quadratic residues. A is a quadratic residue mod P if and only if A and P are relatively prime and there exists an X such that A is congruent to X squared mod P. Now, if P equals 2, there's really nothing to say. If P equals 2, Z mod 2Z star, there's just one number that's relatively prime to 2, namely 1. And 1 is a kth power for all K. So for the prime P equal 2, every number is a kth power and every number has a unique kth root because the only number is 1. So we're going to assume from now on that, because it's the only case which is interesting, is that P is an odd prime. And what does our theorem say in the case of K equal 2? So D, which is K minus 1n, which is D, which is the greatest common divisor of K and P minus 1. Well, K is equal to 2. So the greatest common divisor of 2 and P minus 1. But P is odd. So P minus 1 is even. So 2 divides p minus 1, this is 2. So k equals 2 implies that d equals 2. So A is a quadratic residue modulo p if and only if a to the p minus 1 over 2 is congruent to 1 mod p, and or if and only if the index of a with respect to any primitive root g is congruent to 0 mod 2, which just means the index is always even. So for example, if we take p equal to 7 and we take our primitive root g to be equal to 3, what are the quadratic residues? Mod 7. It's g to all the even powers. G to the 0, g squared, g to the 4th, g to the 6th is 1, so there's nothing to say. So what are these numbers? G to the 0 is 3 to the 0, that's 1. G squared, 3 squared is 9, that's 2. G to the 4th is 81. What is 81? Mod 7 is 4. So the quadratic residues mod 7 are 1, 2, and 4. And the numbers that are not quadratic residues are called quadratic non-residues. And those are all the numbers relatively prime to 7 that are not congruent to 1, 2, or 4, which are 3, 5, and 6. So mod 7, the quadratic residues are 4, and the quadratic non-residues are 3, 5, and 6. So as an exercise right now, I'll give you a few minutes and then I'll try to do it myself. Let's see, take the prime p equal to 11. Find a primitive root mod 11. Find the quadratic residues. And quadratic non-residues, mod 11. And for each quadratic residue A, find all solutions of the congruence x squared congruent to A, mod 11. So that's a nice problem, and that could be the entire midterm exam or next exam even. Not quite, but at least when you know that, you know quite a bit. Okay, let's see. Can anyone tell me what is a primitive root? Mod 11? Well,
2.
yeah, 2. Suppose we take g equal 2. So we know by Euler two to the 10th is congruent to 1 mod 11. Whatever the order of 2 is, it has to divide 10. So the order of 2 is 1, 2, 5, or 10. So this says C. 2 to the first power is congruent to 2, which is not 1 mod 11. 2 squared is 4, which is not 1 mod 11. 2 to the 5th is 32, which is 10, which is not 1 mod 11. So the only other possibility is 2 to the 10th. We know 2 to the 10th is 1 mod 11, so 2 has order 10 mod 11. So 2 is a primitive root. And the quadratic residues mod 11 are the even powers of the primitive root. 2 to the 0, 2 squared, 2 to the 4th, 2 to the 6th, 2 to the 8th.
Professor. Okay, thank you.
So the quadratic residues mod 11 are the even powers of 2 up to 2 to the 8th. 2 to the 10th brings us back to 1. So this set of numbers, mod 11, 2 to the 0 is 1, 2 squared is 4, 2 to the 4th is 16, which is 5 mod 11. 2 to the 6th is 64. What is 64 mod 11? It's 9 mod 11. 2 to the 8th is 256. 256 mod 11 is, I believe, 3. So these are the quadratic residues. And the quadratic non-residues are the odd powers of the primitive root. 2 to the 1st, 2 cubed, 2 to the 5th, 2 to the 7th, 2 to the 9th, which have to be exactly the congruence classes not in this set, which are 2, 6, 7, and 8, and 10 mod 11. So these are the quadratic residues, and these are the quadratic non-residues. And what are the square roots? So remember, the quadratic residues are 1, 3, 4, 5, and 9. So for each of these, we can solve the congruence. What is, for the quadratic residue 1, what are the solutions of x squared congruent to 1 mod 11? Well, you can always use x congruent to 1 mod 11, or x congruent to minus 1, which is the same as 10 mod 11. So 1 and 10 are the 2 square roots of 1. What about x squared congruent to 3 mod 11? Well,
5.
5 is certainly 1, because 25 minus 3 is 22 is divisible by 11. And just as with squares, if x is a square root, so is minus x. So minus 5, which is the same as 6 mod 11, because 36 minus 3 is 33 is divisible by 11. For x squared congruent to 4 mod 11, that's easy. Either x congruent to 2 or x congruent to minus 2, which is the same as 9 mod 11. Because 81, x squared is 81 minus 4 is 77. So what about 5? X squared congruent to 5 mod 11.
4 and 7.
Right, so you can take x congruent to 4, because 16 minus 5 is 11, or x congruent to minus 4, which is the same as 7 mod 11. And again, 9 is very easy. X squared congruent to 9 mod 11. X can be 3, or x can be minus 3, which is the same as 8 mod 11. And 8 squared is 64. 64, take away, oops, let's see, 3. 64 take away 9 is 75. Something is wrong.
Professor,
Sorry, so now, what is funny? So 64 mod 11 is 9. So, oh, right, I'm sorry, so that's okay. 64 minus 9 is 55, which is divisible by 11. So here are my quadratic residues, 1, 3, 4, 5, and 9. And for each of them, there are 2 square roots. And there's the list. Okay, any questions about this? All right. What about some of the homework problems? I'm happy to go over homework problems that you choose, or else I'll choose some myself and do them.
Professor, the 41, can you do plus the quadratic residue of 41?
Which problem was that?
I think it's problem 2, the page, let me check.
Okay, I see. So
Okay, thank
this
you.
is section 3.1. So exercise 1 is to find a primitive root modulo 23. And exercise 2 is to find a primitive root modulo 41. Let me try to do both of them. So exercise 1, find a primitive root modulo 23. So that means G will have order 22 mod 23. And the orders of all integers relatively prime to 23 are the only possible orders are divisors of 22, 1, 2, 11, or 22. So if an integer is not, doesn't have order 1, 2, or 11, it has to have order 22. So let's do the experiment. That is, I'm just going to do trial and error. Suppose I take G equal 2. So G to the first power is 2. As 2 to the first power is 2. That's not 1. G squared, that's 2 squared is 4. That's not 1. This is all mod 23. G to the 11th power. What is that? So that's 2 to the power 11. So I'm trying to find an easy way to do this. If G squared, if 2 squared is 4, let's see, I know that 2 to the 5th is 32, which is congruent to 9 mod 23. 2 to the 6th is 2 times 2 to the 5th is 2 times 9, which is 18 mod 23. 18 is actually the same as minus 5 mod 23. So 2 to the 11th is the same as 2 to the 5th times 2 to the 6th. I'm just trying to get small numbers here. 9 is the same as minus 4 mod 23. So 2 to the 5th times 2 to the 6th is the same as minus 4 times minus 5, which is 20 mod 23. So something here is wrong. So I just have to go back and check what I did. So 2 to the first power is 2 mod 23. 2 squared is 4 mod 23. 2 to the 5th is 32. Oh, sorry, which is the same as 9. Just leave it at 9 because it's not minus 4. So So 2 to the 5th times 2 to the 6th is 9 times minus 5. That's minus 45. And minus 45 is congruent to 1 mod 23. So 2 has order 11 mod 23. So 2 is not a primitive root.
Professor, can you pull the paper up? Okay, thank you.
So I'm just doing it by trial and error. I pick the smallest numbers I can. So mod 23, G is order 22. Or a primitive root, but 2 has order 11. So 2 is not a primitive root. So next we try G equal to 3. So
Professor, can I interrupt for one half second? So when you went to G equals 2, are you just starting at the lowest number that's not 1 when you're
Yeah.
testing? Okay, and then you're just moving up to
I could start
3.
with
and-
17, but it makes the arithmetic much
Right.
harder.
Fair enough.
And I just try and make things as simple as possible.
Great.
So
Thank
I'm
you.
just looking for, unless I have some reason to do anything different, I look for the smallest primitive root I can find.
Great.
So 3 to the first power is 3 mod 23. 3 squared is 9. 3 cubed is 27, which is the same as 4. Let's see. 3 to the 5th power would be 3 squared times 3 cubed. That's 9 times 4, which is 36, which is 13 mod 23. 3 to the 6th power is like 3 cubed squared, because 3 times 2 is 6. 3 cubed is congruent to 4, so that's 4 squared. That's 16 mod 23. So, or minus 7, I guess, mod 23. So 3 to the 11th would be 3 to the 5th times 3 to the 6th. That's 13 times minus 7. That's minus 91 mod 23. Let's see, 4 times 23 is 92. So this is unfortunately also congruent to 1 mod 23. So 3 has order 11 mod 23. 3 is not a primitive root. Right? Now, so we know that 2 to the 11 is congruent to 1 mod 23. Suppose I pick 4. Well, 4 to the 11, 4 is 2 squared. So that's the same as 2 to the 11th squared, which is the same as 1 squared, which is 1 mod 23. So 4 also has order at most 11. So 4 is not going to work. So the next number to try is 5. 5 to the 1st power is congruent to 5 mod 23. 5 squared is 25, which is 2 mod 23. That means 5 to the 4th is 5 squared squared. That's 2 squared. That's going to be 4 mod 23. 5 to the 5th is 5 times 5 to the 4th. That's 5 times 4, which is 20, which is minus 3 mod 23. 5 to the 6th is 5 times 5 to the 5th, which is 5 times minus 3, which is minus 15, which is 8 mod 23. 5 to the 11th is 5 to the 5th times 5 to the 6th. That's minus 3 times 8, which is minus 24, which is minus 1 mod 23. So 5 does not have order 1, 2, or 11. That means 5 must have order 22. So 5 is a primitive root. So this is one primitive root. There are phi of 23 minus 1, phi of 22. That's how many primitive roots there are. And phi of 22 is phi of 2 times 11. That's phi of 2 times phi of 11, because phi is multiplicative. Phi of 2 is 1, so this is phi of 11. 11 is a prime, so phi of 11 is p minus 1. So in fact, modulo 11, there are going to be 10 primitive roots. And we just found one, and we could find more, obviously, because in fact, almost half of the numbers are primitive roots. That's kind of interesting.
Professor, one question.
Yeah,
How many primitive roots are we supposed to find? Are we expected to find?
no. So the problem says find a primitive root.
Oh,
So that just means find one.
all right.
And, I mean, if you guess at random, almost half of the numbers in this instance are primitive roots. But so you might make a lucky guess, but it's not the most reliable way to solve the problem. But in any case, the point is that these are interesting problems. You actually have to do some work to solve them. So let me go to the problem I was asked, which is exercise 2. To find a primitive root mod 41. So phi of 41 is 40. So every a to the 40th is always congruent to 1 modulo 41 for every number a that's relatively prime, that's not divisible by 41. So the possible orders of elements mod 41 are the divisors of 40. And unfortunately, there are a lot of them. 1, 2, 4, 5, 8, 10, 20, and 40. So there are 8 possible orders, and a primitive root is going to have order 40. It won't have order 1, 2, 4, 5, 8, 10, or 12. So let's start by trying g equal 2. So what are the powers of 2 mod 41? 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. So 2 doesn't have order 1, 2, 4, or 5. What about 2 to the eighth? So let me try and be lazy about this. 2 to the fifth is 32, which is minus 9 mod 41. So 2 to the eighth is 2 cubed times 2 to the fifth. 2 cubed is 8. 2 to the fifth is minus 9. So this is minus 72. Let's see. 2 times 41 is 82. So this is the same as 10 mod 41. So 2 to the eighth is not 1. 2 to the 10th is 2 squared times 2 to the eighth. 2 to the squared is 4, and 2 to the eighth is 10. So this is 40, which is minus 1 mod 41. But then 2 to the 20 is 2 to the 10 squared. So that's minus 1 squared, which is plus 1. So 2 has order 20. It's not a primitive root. It doesn't have order 40. Okay. So, I mean, I'm doing this calculation a little bit quick because there's a lot of calculation, but this is essentially elementary school arithmetic, but a little bit harder than elementary school. So let's try g equal 3. I can't think of any reason to try a more complicated number next. So what are the powers of 3? Mod 41. 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. Let's see, 2 times 41 is 82. So this is like minus 1 mod 41, which means exactly that 3 to the 8th power, which is 3 to the 4th squared, will be minus 1 squared, which is 1 mod 41. So 3 has order 8. It doesn't have order 20. Three has order 8. So we have to keep looking. If 2 has order 20, 4 has order 20, because raise 4 to the 20th power, it's just like raising 2 to the 20th squared power, and 2 to the 20th is 1. So let's try g equal 5 next. So what are the powers of 5 mod 41? 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. 125 mod 41. Let's see. 41 times 3 is 123. So this is congruent to 2. Mod 41. Now, we saw that 2 has order 20. Let's look. 5 to the 4th. Let me just keep going. 5 to the 4th is 5 to the first times 5 cubed. That's 5. 5 cubed, according to this, is 2. 5 to the 4th is 10. Mod 41. 5 to the 5th is 5 to the 4th times 5. That's 10 times 5, that's 50, which is 9. Mod 41. 5 to the 6th is 5 cubed squared. 5 cubed is 2, 2 squared. That's 4 mod 41. So again, I'm not sure that, let me just double check everything on I did. Mod 41. 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. Subtract 2, that's 123, which is 41 times 3. 5 to the 4th is 5 times 5 cubed is 10. 5 to the 5th is 5 to the 4th times 5 is 50, which is 9. 5 to the 6th is 5 cubed squared, which is 4. So, I'm sorry, this is okay. I mean, I'm not sure why I want that. 5 to the 10th is, well, let me just do it like this. 5 to the 4th times 5 to the 6th. 5 to the 4th is 10. 5 to the 6th is 4. That's 40, which is minus 1 mod 41. So 5 to the 20th is 5 to the 10 squared is minus 1 squared is 1 mod 41. So 5 has order 20 mod 41. So we're not having a string of good luck here. 5 has order 20. It doesn't have order 40. So what should we try after 5? I don't know. I guess we could try 6. Now, we already know 6 is 2 times 3. And we saw that the order of 2 is 20, and the order of 3 is 8. So the order of 2 is 20, the order of 3 is 8. So let 6 have order k. So 6 to the k is congruent to 1 mod 41. And 6 is 2 times 3. So that means 2 to the k times 3 to the k is congruent to 1 mod 41. So I'm trying to avoid doing a lot of calculation. I'm not sure I'll be able to. Suppose I raise everything to the 20th power. So if I raise this to the 20th power, that's this to the 20th power, which is still 1. So 2 to the 20k times 3 to the 20k is congruent to 1 mod 41. But 2 to the 20th is 1. So this says, so 2 to the 20th congruent to 1 mod 41 means 3 to the 20k is congruent to 1 mod 41. And 3 has order 8. So 8 has to divide this. So 2 divides k. So this isn't going to work out the way I hope, but it's not a bad idea, I think. But in any case, we still haven't solved the problem. So we could try g equals 6 or g equals 7. Let's try g equals 6. I have no idea what's going to work. 6 to the first power is congruent to 6. 6 squared is congruent to 36, which is minus 5 mod 41. 6 cubed is 6 times 6 squared, which is 6 times minus 5, which is minus 30, which is the same as 11 mod 41. 6 to the fourth is, I don't know, 6 squared squared. That's minus 5 squared. That's 25 mod 41. Six to the fifth, maybe I'll write that as 6 squared times 6 cubed. 6 squared is minus 5. 6 cubed is 11. So that's minus 55. Modulo 41, that's like minus 14 mod 41. Remember, I have to try the exponents 1, 2, 4, 5, 8, 10, 20, and 40. Those are the possible orders. So I can see 1, 2, 4, and 5 don't work. 6 to the 8th. What should I do with 6 to the 8th? Let's see. Well, 6 to the 8th is 6 cubed squared. That's 11 squared. That's 121. 3 times 41 is 123. So this is minus 2 mod 41. So 6 to the 8th is 6 squared times 6 to the 6th. 6 squared is minus 5. 6 to the 6 is minus 2. So this is 10 mod 41. 6 to the 10 is 6 squared times 6 to the 8th. That's minus 5 times 10 is minus 50 is minus 9 mod 41. 6 to the 20th is 6 to the 10 squared. That's minus 9 squared. That's 81 is minus 1 mod 41. And I finally have an answer because 6 does not have order 1, 2, 4, 5, 8, 10, or 12. And of course, 6 to the 40th is 6 to the 20 squared is minus 1 squared is plus 1 mod 41. So 6 is a primitive root, right? Whew. That's what it is. Kind of interesting. Yeah, I don't know any shortcut. In general, finding a primitive root is hard, but it is interesting.
Professor,
Yeah,
can you go over another homework problem?
of course.
It's page 100, problem 3 and 4, if you can.
Okay.
Thank you.
So this is section 3.3, exercise 3. Sorry, exercise 4. Which
Three
one
and-
did you?
Both of them, 3 and 4, if you can.
Well, let me start with 4. So find the 5th power residues modulo 11. So we already found a primitive root mod 11, I think. So 2 is a primitive root mod 11. So we're interested in 5th power residues, k equals 5. Our prime is 11. D is the greatest common divisor of k and p minus 1. That's the greatest common divisor of 5 and 10, which is 5. And so the theorem 3.11 says that A is a 5th power residue modulo 11 if and only if let's see, A is so if and only if the index of A with respect to 5 is congruent to 0 mod D, mod 5. So if and only if the index of A is a multiple of 5. Is 0 or 5. So A is either 2 to the 0, which is 1 mod 11, or A is 2 to the 5th, which is 32, which is minus 1 mod 11, or 10 mod 11. So the 5th power residues modulo 11, that is the only numbers whose 5th powers are 1 mod 11, oh, sorry. The only numbers that are 5th powers are 1 and minus 1. So we have 1 is congruent to 1 to the 5th mod 11, and 10 or minus 1 is congruent to 10 to the 5th mod 11. This is the same as saying that minus 1 is congruent to minus 1 to the 5th mod 11. So there are two 5th power residues mod 11, and they're 1 and 10. All right. The idea is A is a 5th power residue if and only if A is congruent to x to the 5th mod 11 for some x. And if we write A as 2 to the L and x as 2 to the y, this is 2 to the 5y is congruent to x mod 11, which is the same as saying 5y is congruent to L mod 10, which is the same as L is congruent to 0 modulo the greatest common divisor of 5 and 10, which is 5. So if and only if L is equal to 0 or 5, mod 10, and that gives you L equals 0 gives you 1, and L equal 5 gives you 32, which is 10 or minus 1. Right? So that's actually using our theorem to solve the problem. And what was the other question you asked about?
Number 3.
Okay. So this is section 3.3, exercise 3. We have the non-zero congruence classes modulo 19, and we define a function f from this multiplicative group to itself. So define the map or the function by f of the congruence class x plus 19z is going to be x cubed plus 19z. So we're cubing. So prove that f is a homomorphism. So this is a multiplicative group. And to say F is a homomorphism, if and only if I take F, apply to the product of two congruence classes, that's F of the first times F of the second. But the product of these two congruence classes is xy plus 19z. So this is equal to xy cubed plus 19z, which is x cubed y cubed plus 19z, which is the product of x cubed plus 19z times y cubed plus 19z. And this is f of x plus 19z, and this is f of y plus 19z. So from the definition of a homomorphism and the definition of the product of congruence classes, this function is a group homomorphism. And the kernel is everything that gets sent to the identity. So this is all x plus 19z, such that f of x plus 19z is 1 plus 19z. So this is all x plus 19z, such that x cubed plus 19z equals 1 plus 19z. So this is all x plus 19z, such that x cubed is congruent to 1 mod 19. So the kernel of this homomorphism is all of the cube roots of 1. All the numbers such that x cubed is congruent to 1 mod 19. So we have to solve the congruence. X cubed congruent to 1 mod 19. So it would be helpful to have a primitive root mod 19. And then if x is g to the y, then we want to solve x cubed, which is g to the 3y, g to the y cubed, congruent to 1 mod 19, which means 3y has to be congruent to 0 mod 18, which means y is congruent to 0 mod 6. So the solutions of this congruence are g to the 0, which is 1, because 1 cubed is 1, g to the 6th, and g to the 12th. So if you calculate a primitive root mod 19, whatever it might be, then the three solutions of this congruence are g to the 6th, or 1, g to the 6th, and g to the 12th. And that gives you the kernel of that function that we just defined. So there still is some work to do. You have to find a primitive root mod 19, but then you're done.
Thank you, Professor.
Right. Okay, well, I guess that's it for this morning. See you on Wednesday. Any questions before we end? Okay.
Yeah, one question. Well, the meeting times will be posted online, right?
Sorry?
Well, the meeting times, they'll be posted, office hours, they'll be posted online, right?
Yeah, I'll do that. Actually, I'll try and do it as soon as I log off and get this lecture recorded. So by 11 o'clock, it'll be posted.
So will there be any office hours for today, or
Actually, I'm open to your suggestions. Is there a time you would prefer?
sure, 11 o'clock?
Sorry?
11 o'clock.
Well, no, I have a class from 11 to 1.
Oh. So I guess I'll wait for the office hours you post online then.
Okay, all right. All right. Okay, take care all.
Take care, Professor. Have a good day.
Take care, Professor. Thank you.
Thank
Right,
you,
bye-bye.
Professor.